Okay, let's try this as a test. So if I want to do an actual rigorous proof for you guys, here is one. So figure out how to actually draw on this thing. Okay. Yeah. Here's a proposition. For all a in the integers, a times 0 equals 0. Now, before I actually jump into the proof, I do want to mention the idea, like, why is this true? And okay, so what we would do is I would think about the number line, and I would think about scaling everything by a, right? So like here's a times 1, here's a times 2, here's a times 3. And so you're actually taking, maybe, let me draw another copy of the number line. You're actually taking the numbers 1, 2, 3 and scale, scale by a, right? By a factor of a. Okay, but if you think about that, it's easy to keep going with this number line, right? 0, -1, -2, and so on. So this distance, this distance right here is 1. This distance is 1. But this distance here now, it's been scaled, so that's a. And that's a. And so this if I go, this one is a right here, right? This one is a, and so I'm hopping around by a's. So you could imagine that, I have a times 0 here, a times -1, and a times -2, and so on. This is a, here, right here, this is actually, 2a is 1 plus 1 times a, which is 1 times a plus 1 times a. I'm just trying to be kind of rigorous like this, which is a plus a, right? So it kind of makes sense that's actually why I'm saying this is a right here. And this is a, that you can sort of justify that to go from a to 2a, you're actually adding a, right? I have to add another a to get 2a. And so these are all going to be equally spaced. This is going to be a. And if you just think about what's going to happen if I move by a this way, where do I expect? Oh, it doesn't really look good with the laser pointer, does it? If I'm moving by a this direction, then what do I actually expect this value to be? Well, this is a right here. This is a plus a plus a plus a. And I'm hopping by a's. And so, in fact, this really should equal 0. So I guess the idea is that when you're multiplying by a, you're scaling the whole number line by the same factor, and so everything that's possible gets scaled up by a. But it kind of like, if everything is now a apart, where before it was 1 apart, then there seems to be no choice but for a times 0 to land exactly at 0, right? So that's the idea. And then the real thing what is it? Why does this happen? Why does the number line get scaled by a factor of a where everything is now a apart? Well, that actually really comes down to the distributive law. This was the distributive law right here. In fact, this equal sign right here, right? It's the distributive law is kind of the key to this. Which makes sense because it's the only axiom we have that directly relates the multiplication to the addition, right? Okay, so I claim that's going to be important in the proof too. So let me go to the next page. So the actual proof is, well, I want to show, I mean, maybe let's look at it this way first. We want a times a0 to be 0, so we want a times 0 to act like an additive identity. Fair enough, right? So that means we want a times 0 plus a to equal a. We'd like to show that. And okay, so there's a question mark right here, and I'm saying we don't know this, we haven't established this is to be true yet, but we want this to be true. So that when we add a times 0 to a, we actually don't change the value of a. Well, so, okay, so when you're trying to show two things are equal, I actually think, some students like to kind of take this and move it down till, keep doing steps till they get a two things being equal to each other that are obviously equal, like 0 equals 0 or something. But that's actually a backwards proof. So here I prefer to actually start with the left-hand side and try to turn it into the right-hand side. So start with left-hand side, turn into the right-hand side. So let's consider a times 0 plus a. Well, it's very tempting to factor an a out of that, but we can't quite do that till we have the second a, this a being a times something. And that's clearly a times 1, right? So a times 0 plus a times 1 equals, oh, sorry, oops. Let me do this right. This is a times 0 plus a equals a times 0 plus a times 1 by the multiplicative identity axiom, right? That we can sort of rewrite a times 1 as a. So multiplicative identity axiom. And now we can use the distributive law. That's a times 0 plus 1 by the distributive law. Which equals a times 1, because 0 plus 1 equals 1, that's by the additive identity axiom. And that equals a by the multiplicative identity axiom again. Okay, so that, yeah, that gets us that a, so a plus, a times 0 plus a equals a. So this implies this implies this implies this. Now we're not quite done because we actually really want to show a times 0 equals 0 rigorously. There's an alternate argument where you say, well, anything, you can sort of show that the additive identity is unique so that anything that acts like an additive identity has to equal the additive identity. So once you have this equation established, you could then say, well, that forces a times 0 to equal 0 because a times 0 is behaving like an additive identity there. It's actually a little bit, it's a little bit more elegant, I think, than what I'm about to do, but let's just do it the long way. So let me go to the next page. So just to show you the long way. Okay, so page 3. Let's see. So just continued. Let's see, the proof is continued for the previous. Okay, a times 0 plus a equals a. Well, let's add, we want to get a times 0 equals 0, right? So we really need to subtract a from both sides, but the only way we can do that is by adding negative a to both sides, right? A times 0 plus a plus negative a equals a plus negative a. That's just by adding the same thing to both sides of an equation. We can sort of do that without comment. And then now we have to associate our parentheses to get a plus negative a together. That's by the associative law. And then that means now we can apply the additive inverse axiom to cancel a plus negative a. So that's by the additive inverse axiom. And that implies, well, now we can sort of get rid of this 0 right here by appealing to the additive identity axiom. So that implies a times 0 equals 0 by the additive identity. And that's what we wanted to prove. So therefore QED, that's the end of the proof. Okay, we use a little box, like a square box. I like to use this for the end of proof symbol. And so we're done. Okay, I'll stop there.